Black holes represent one of the most profound concepts in our understanding of the cosmos. They are not objects in the conventional sense, but rather the consequence of space-time being warped to an absolute extreme. This profound distortion gives rise to phenomena so unusual they can challenge our fundamental perception of how the universe works. The science behind them is so strange that it might seem like fiction, yet it is firmly grounded in rigorous mathematics, with a growing body of observational evidence confirming that these calculations accurately describe reality. We can embark on an exploration of these cosmic enigmas, delving into the science of their formation, the bizarre environment that surrounds them, and the theoretical possibilities of escaping what seems to be the ultimate prison. Black holes manifest across an astonishing range of scales. The least massive one observed to date is approximately 3.8 solar masses. At the other end of the spectrum are colossal black holes that formed in the early universe, weighing as much as billions of our suns. These ancient behemoths are not only incredibly massive, but also immense in size. The diameter of their event horizon could comfortably contain our entire solar system. The black holes that form in the modern universe are the final evolutionary stage for the most massive stars. Throughout its life, such a star exists in a delicate equilibrium between two powerful, opposing forces. The first is gravity, which exerts a constant crushing pressure, pulling all the star's matter inward toward its center. Deep within the stellar core, this immense pressure forces hydrogen atoms together, causing them to fuse into a denser element, helium. The resulting atomic structure requires less energy to maintain than the two separate hydrogen atoms did, so the surplus energy is released. This liberated energy constitutes the second force, radiating outward from the core as heat and light, perfectly counteracting the inward pull of gravity. A star will remain in this stable state for millions or billions of years until it begins to exhaust its primary hydrogen fuel. For a sufficiently massive star, the depletion of hydrogen triggers a new phase. It begins fusing the newly created helium into even heavier elements, such as carbon, neon, and eventually oxygen and silicon. But this process ultimately leads to the fusion of iron. The critical issue with iron is that its formation does not result in a net release of energy. It simply accumulates in the star's core, a growing, inert mass. Without the outward pressure from fusion energy to resist gravity, the delicate balance is irrevocably broken. The ensuing collapse releases an almost unimaginable amount of energy, with the force being directly proportional to the star's original mass. As the star's outer layers plummet inward and strike the dense iron core, the impact generates a cataclysmic rebound, an explosion we call a supernova. In one of the most violent events possible in the universe, matter and energy are blasted outward, forging elements even heavier than iron, all the way up to uranium. The fate of the stellar remnant depends entirely on its mass. If the star's initial mass, and therefore the force of its collapse, was below a certain threshold, the remnant becomes a neutron star. This is a compact sphere of matter, perhaps only 25 kilometers across, yet so incredibly dense that its mass is equivalent to 1,000,000 Earths. But if the original mass and the resulting force were great enough, our current understanding of physics breaks down, leaving behind a black hole. When we view an illustration of a black hole, the dark sphere is not the object itself. Scientists theorize that the true essence of a black hole is a singularity, a structure likely even smaller and denser than a neutron star. It is thought to be a point of infinite density and infinitesimal size, from which emanates a force that warps space and time. However, this remains a theoretical concept, as we cannot directly observe it due to the presence of the event horizon. Every object with mass generates a gravitational field, a principle understood since the time of Newton. But in 1915, when Einstein presented his theory of general relativity, a physicist named Karl Schwarzschild used its equations to deduce the possible existence of objects so massive that their gravitational pull would be strong enough to trap light itself. And if even massless photons of light could not break free, then nothing else could. The image of a black hole is therefore not of the singularity, but of the event horizon surrounding it. This is the ultimate boundary, the line where gravity becomes so overwhelmingly powerful that light can no longer escape, resulting in absolute darkness. The influence of a black hole extends beyond just space. It also dramatically affects the fabric of time. According to Einstein, space and time are inextricably linked into a single continuum called spacetime, which is distorted by mass. The singularity, with its theoretical infinite mass, stretches spacetime to such a degree that the event horizon also becomes the point where time itself appears to stop. Inside this boundary, the familiar concepts of space and time effectively cease to exist. It is a region with no where or when. This leads to a curious effect for an outside observer watching an object approach a black hole. From their vantage point, the object would seem to slow down as it nears the event horizon, eventually appearing to freeze just outside of it. An observer would never witness it actually cross the boundary or be absorbed. Instead, the object would just grow progressively dimmer until it faded from view entirely. When first proposed, many astronomers and physicists were skeptical about the real-world existence of black holes. The first tangible evidence did not emerge for another 40 years. In 1964, using newly deployed X-ray satellites, astronomers detected a powerful source of X-rays in the constellation Cygnus. What was peculiar was that no visible object could be seen at the source of these emissions. This was surprising, as a star emitting such intense X-rays should also be radiating visible light. Scientists designated this mysterious object Cygnus X1. By 1970, with more advanced telescopes, it was discovered that Cygnus X1 was in a binary orbit with another star. This orbital relationship was key, as it allowed astronomers to calculate the invisible object's mass. Their findings were remarkable. The object was 15 times more massive than the Sunday. Given that the theoretical upper limit for a neutron star's mass is about 3 times that of the Sun, scientists concluded that they had likely found the first observational evidence of a black hole. Since that landmark discovery, many more black holes have been identified throughout the cosmos. It is understood that supermassive black holes reside at the very center of most galaxies, and we have even succeeded in imaging some of them directly. These images reveal a profound darkness outlined against a glowing, swirling band of material that surrounds it and spirals inward, what is known as its accretion disk. This disk is precisely how black holes can be indirectly observed through X-rays. Although a black hole itself cannot emit any visible electromagnetic radiation, the X-rays associated with it actually arise from this surrounding accretion disk. Within this disk, infalling matter is subjected to such intense friction that it heats up to millions of degrees Celsius. Consequently, a black hole that is not actively feeding on nearby material would lack a luminous accretion disk, rendering it effectively invisible to us. The study of black holes remains a developing area within physics, with a great deal yet to be discovered. Based on what has been uncovered so far, one might question whether a black hole can ever cease to be what it is, or if its fate is to grow indefinitely until all matter and radiation in the cosmos are consumed. The latter would seem to be the case. However, a pivotal shift in thinking occurred in 1974, when the physicist Stephen Hawking published a paper that explored the question of whether black holes could, in fact, explode. In it, he postulated that there was indeed a mechanism through which energy, and therefore mass, could escape from a black hole. To comprehend his reasoning, though, we must delve into some deeply counterintuitive theory. It requires an examination of certain principles from the realm of quantum mechanics. But as a starting point, consider a challenging question. What is the true nature of nothing? Picture for a moment an area of space that is completely empty. It contains no atoms, no particles of cosmic dust, and not even a single ray of radiation is passing through it. By all appearances, nothing whatsoever exists within this volume. And yet, is it genuinely and truly empty? The answer, it turns in, is no. Something fundamental is present there, a fact we can infer from the behavior of a beam of light traveling through it. If you are acquainted with the properties of light, you will know that it consists of waves of electrical and magnetic charge, which continuously propagate one another forward in a straight line. Let's pause, however, on that specific word, wave. A wave in the ocean is the movement of energy through the medium of water. If you were to observe a single water particle, you would see it is not really traveling anywhere, but is instead moving in a small circle. Yet, because it transfers its energy to adjacent atoms, that energy journeys toward the coast in a continuous motion that carries it all the way to the shore. In a similar fashion, A sound wave advances by passing energy from one air particle to the next, with each particle moving only a minuscule amount, becoming energized and then conveying that energy to the subsequent particle in the sequence. But in our vacuum of space, a volume containing nothing, where our photon of light is traveling in waves, it is worth asking what, precisely, is doing the waving. This points to a fundamental something that persists even in a perfect void, a kind of fabric that constitutes all of reality itself. Quantum physicists refer to this something as a quantum field. Quantum fields are notoriously difficult to conceptualize, but they are absolutely essential for understanding the ultimate fate of a black hole. So what is the connection between quantum fields and the idea of exploding black holes? Returning to Hawking's paper, his hypothesis was that black holes would gradually release energy over vast timescales, beginning in incredibly small amounts. Since energy and mass are two different expressions of the same phenomenon, according to Einstein's famous equation E equals mc2, this process would inevitably lead to a decrease in the black hole's total mass. But as the black hole shrinks, the rate of this energy emission would accelerate, getting progressively faster. This would continue until the final moments of the black hole's existence, when it would unleash a burst of energy of truly gargantuan proportions before disappearing completely. But how could this possibly be true? It is a well-established principle that nothing can escape an event horizon, so how could any radiation ever depart from it and ultimately trigger such a cataclysmic explosion? The explanation is a strange one, rooted in unintuitive concepts from quantum theory that run entirely contrary to our everyday experience. If this theory holds, then the universe is a far more peculiar place than you might have initially imagined. To begin to grasp Hawking's theory, we must first understand the concept of quantum fields. Recall that light behaves like a wave even as it moves through a completely empty region of space, which suggests there must be something present even in a vacuum. Otherwise, there would be no medium for the light to wave. Scientists call this underlying fabric of reality a quantum field. In fact, the current understanding is that there are multiple quantum fields, all overlapping one another and extending throughout every single point in the universe, across all of past, present, and future. Each distinct quantum field corresponds to a particular type of particle or force. For instance, one field might define all existing electrons, while another could define the quarks that form the components of an atom. In a region where nothing can be detected, the quantum field is in a relatively calm state. You can imagine it like a guitar string that has not been plucked, or a line on a graph that rests at a zero value. But at any point in space and time where mass or energy is present, the quantum field is resonating at that location. When this resonance reaches a specific threshold or quantity, the universe manifests it as, for example, an electron or a photon. It is crucial to recognize that in this model, the resonance is not merely a reaction to a piece of matter. The resonance times is times the matter. An electron is understood to be nothing more than a resonating portion of the quantum field that defines electrons. This principle applies to all energy and all matter after all. According to Einstein, they are two sides of the same coin. The entire universe you observe around you is simply a collection of resonating quantum fields, and nothing else. Seen this way, the theory paints a picture of the cosmos as a song being played across these fundamental fields, which is quite a beautiful image. But what is the significance of this? Why is it so important to define the universe in this manner? The reason lies in a concept from quantum physics known as Heisenberg's uncertainty principle, which suggests that sometimes the strings of the universe can begin to vibrate on their own. Without delving too deeply into this particular aspect of quantum physics, the principle essentially states that when we observe extremely small objects at the atomic scale, it becomes impossible to know certain properties about them with complete precision. For instance, you cannot simultaneously know both the exact position and the exact direction of travel of an electron. Because the particle is so tiny, the very act of trying to measure its location will inevitably disturb it, causing it to bounce off whatever instrument is used for the measurement, which in turn makes its direction of travel uncertain. Conversely, if you know its direction with certainty, this principle dictates that you cannot know its precise location. This limitation is not a result of our measurement techniques being inadequate. Rather, it stems from the fundamental laws that govern the nature of the universe itself. Heisenberg's uncertainty principle suggests that at the subatomic level, a complete and simultaneous knowledge of a particle's properties is fundamentally unattainable. When this concept is applied to quantum fields, the implications become even more profound. These fields are in a constant state of fluctuation throughout the cosmos, and because of the uncertainty principle, this allows for pairs of particles and their antimatter counterparts to spontaneously emerge from the vacuum. While the specific mechanics are intricate, the universe essentially permits this fleeting existence, as long as the pairs vanish within an extremely brief period dictated by the uncertainty relations. It might seem implausible that matter could simply spring into being from nothing. Surely, such an event would have been observed by now. However, an experiment by Hendrik Casimir offered compelling evidence that this strange phenomenon may indeed be real. Casimir arranged two conductive metal plates to be exceptionally close to each other, creating a space where only virtual particles of certain smaller wavelengths could form between them, thereby limiting their total number. In the area outside the plates, by contrast, particles of all possible wavelengths could appear without restriction. This imbalance established a difference in pressure. The greater population of virtual particles on the outer surfaces exerted more force than the limited number on the inner surfaces. Just as the theory predicted, this external pressure was observed to push the two plates together. The notion of particles materializing from the void appears to challenge the law of conservation of matter, and for good reason. To maintain cosmic balance, whenever a virtual particle is created, it is always accompanied by an antiparticle. If one imagines the matter particle as a 1 on a universal ledger, its antimatter partner acts as a negative 1, which ensures the net value remains a perfect 0, keeping the universe's accounts in order. Furthermore, these pairs exist only for a moment before they collide and annihilate one another, returning to the emptiness from which they arose, which is why we are typically oblivious to this constant quantum activity. A fascinating side theory proposes that antimatter is merely ordinary matter, moving backward through time, but exploring that degree of strangeness is not essential here. The crucial point is that quantum fields are perpetually resonating and, for the most part, perfectly cancelling themselves out, which is why empty space appears to us as empty. But this leads to a compelling question. What might occur if only some of those resonating fields were suppressed? This is precisely the scenario that brings black holes into the picture. A black hole can be seen as an object that disrupts the perfect, balanced resonance of the universe's quantum fields. Due to their event horizons, certain fluctuations are effectively dampened, while others are left to continue unimpeded. Stephen Hawking considered this very idea with a thought experiment, envisioning a line through space-time that included the formation of a black hole within a specific region. He imagined a quantum field resonating along this timeline, stretching from a point before the black hole came into being to a point far into its future. In the era before the black hole's genesis, everything proceeds as expected, with quantum fields fluctuating freely and their effects neatly negating one another. The emergence of the event horizon, however, fundamentally altered the local curvature of space. In this new geometry, Hawking realized that certain quantum pulses outside the event horizon were now without their cancelling counterparts. As he examined the mathematics, he saw that after the black hole had formed, the perfect cancellation was no longer taking place. Instead, he found resonances traveling away from the event horizon that possessed the exact mathematical signature of thermal radiation streaming out into space. Radiation is a form of energy, and energy cannot be created out of nothing. If a black hole was producing this radiation, it would need to pay an energetic cost. Therefore, each particle of this Hawking radiation would have to correspond to an equivalent loss of energy from the black hole itself. Over immense timescales, this slow but steady leak of energy would cause the black hole to shrink until it was ultimately reduced to nothing. If Hawking radiation exists, its mechanism is somewhat like money, spontaneously appearing outside a bank, while an equal amount of cash vanishes from the vault inside. Proving its existence is also an extraordinary challenge. Hawking's calculations predicted this radiation would be colder than the cosmic background radiation that already permeates the universe, and its wavelength would be as long as the black hole's event horizon itself. Considering that some black holes have event horizons the size of entire solar systems, we currently possess no way to detect such a faint, long wavelength signal. We could likely only observe it clearly once the universe itself had grown cold and dark, with no other radiation to interfere, a time when we would almost certainly no longer be around to build the detector. Yet, in spite of these observational hurdles, the mathematical theory behind Hawking radiation is considered exceptionally sound. More recently, scientists have taken innovative steps toward demonstrating it in a laboratory. At the Technion Israel Institute of Technology, a team of researchers investigating Hawking radiation conceived of an ingenious method to circumvent the difficulty of measuring a real black hole. They accomplished this by creating an analog, a sonic black hole engineered to mimic the properties of a gravitational one. Their approach relied on the fact that sound travels much more slowly than light, which makes it far easier to create a medium that moves faster than the speed of sound. In this system, any sound waves traveling with the flow could never escape it, effectively creating a sonic event horizon. What stands out is that Hawking's equations applied just as well to these sonic black holes as they did to gravity-based ones, implying that a sonic version of Hawking radiation should be detectable. After running their experiment 97,000 times over 124 days of continuous data collection, the researchers detected multiple instances of this analog radiation, and they saw that it matched the predictions of Hawking's model for how it should behave. Although this result does not prove that Hawking radiation is real for actual black holes, the fact that the mathematics held true in this physical analog provides a strong implication that he was on the right path. Hawking radiation may very well be a real phenomenon. So, if you were to fall into a black hole, could you ever escape? Probably not. However, if you could wait until near the end of the universe, the black hole might just radiate away through this process until the mass and energy that made up your existence were entirely removed from inside the event horizon. Whether that counts as an escape is perhaps not so appealing. The best advice is simply not to go in. And this is not the only peculiar thing about black holes. Their existence points to something quite worrying about our own reality. When you are walking on a beach and you make a footprint in the sand, there is no question in your mind that it is your foot that caused the footprint. The sequence of cause and effect appears utterly straightforward, almost too simple to require stating. A foot impresses itself upon the ground, leaving a footprint. The footprint does not, in turn, create the foot. Yet, what if this fundamental link between an action and its consequence could be less distinct than our intuition suggests, particularly on a cosmological scale? It is a startling proposition, but the nature of black holes and the phenomenon of Hawking radiation offer compelling hints that this might indeed be the case. To begin exploring this idea, we must first turn our attention to a principle known as relativity. Though perhaps not the one that immediately comes to mind, our starting point is Galilean relativity, a concept first articulated by Galileo Galilei in 1632. The central idea of this form of relativity is that there is no perceivable difference between a state of complete rest and one of continuous, unvarying speed. Let us consider two chambers, one situated on a ship and the other on land. Both are perfectly soundproof and devoid of any windows. If we imagine the sea as exceptionally calm, eliminating any rocking motion, the only distinction between these two rooms is that one is in motion while the other is not. From inside, would it be possible to tell which is which? One might assume that the sensation of movement would be detectable, but this is not so. For instance, at this very moment, you are traveling through space at a speed of 110,000 kilometers per hour as the Earth orbits the Sunday. And yet, if you are seated quietly at home, you would likely describe your state as being perfectly still. Galileo understood that no conceivable experiment performed within these rooms could reveal the difference between the two situations. He even reasoned that if you were to drop a ball inside the moving ship, it would appear to you to fall in a straight line to the floor. An observer on the shore, however, would see that same ball trace a diagonal path through the air. Galileo's profound insight was that in the absence of external frames of reference, such as when floating in deep space, there is no absolute way to determine if a planet is moving toward you or if you are moving toward the planet. Within the framework of relativity, both perspectives are considered equally correct. You may have experienced a similar effect yourself when looking out the window of a train, just as another train on an adjacent track begins to pass. Even though both are moving forward, the other train's greater speed can create the illusion that you are suddenly moving backward because your immediate frame of reference has been altered. Albert Einstein took this concept and expanded upon it with his equivalence principle. He, too, used the idea of two rooms, but his observation was focused on the nature of gravity. Imagine being inside a windowless room adrift in the vacuum of space. If a rocket were attached to the bottom of this room and began to accelerate it in the up direction at just the right rate, the sensation inside would be identical to standing in a room on the surface of the Earth. In essence, there is no way to distinguish between the acceleration produced by gravity and the acceleration generated by a rocket, provided one could ignore the vibrations of the engine. Both of these principles are rooted in the concept of inertia, the tendency for an object at rest to remain at rest, and for an object in motion to continue that motion. Whenever a mass is required to do something different from what it is already doing, a new force must be introduced. Otherwise, its state will remain unchanged. But this raises a question. Why would the person in the accelerating room feel as though they were experiencing gravity? Or, perhaps more accurately, why do we, on Earth, feel as though a rocket is constantly accelerating us upward? Surely the Earth is not expanding outward in all directions, pushing us along with it. While that is not happening, Einstein recognized that the two scenarios felt alike because they were, fundamentally, the same phenomenon, a form of acceleration. There is, however, another type of acceleration that provides a better model for gravity than the simple push of a rocket. Consider a spinning amusement park ride. Anyone who has been on such a ride understands the powerful feeling that comes from constantly changing direction. As the ride reaches its full, constant speed, you feel a persistent force pinning you against the outer wall. This occurs because your body's mass is continuously trying to travel in a straight line. The ride's curved wall, however, constantly forces you to change your direction. The force you feel is the result of the conflict between your inertia, your resistance to change, and the wall altering your path. And from the perspective of acceleration, there is little distinction between the ground beneath you, accelerating you upward, and you attempting to accelerate downward. Einstein realized that this type of acceleration, one caused by following a curved trajectory, was the true explanation for gravity. He developed a theory in which matter and energy warp the very fabric of space around them, much like a heavy ball would distort the surface of a stretched rubber sheet. The greater the mass, the more significant the curvature it creates. Consequently, any object attempting to travel through this curved space would have its path deflected by that distortion. The physicist John Wheeler famously articulated this relationship by stating that space dictates the motion of matter, while matter instructs space on how to curve. For smaller masses, this warping of space is very subtle. But for incredibly dense masses, the curvature can become so extreme that any object venturing too close will find escape impossible. These are the conditions that give rise to a black hole and its event horizon. Returning to our original analogy of the foot and the footprint, if a black hole is the foot, then the curvature of space surrounding it is the footprint. It is fascinating to see these principles in action and to appreciate how Einstein arrived at conclusions that have been overwhelmingly confirmed by scientific observation for over a century. Yet, so far, nothing in this description is particularly strange. Understanding the precise mechanics does not make the process itself counterintuitive. The black hole tells space how to curve, and the curved space then tells other objects how to move. This chain of events aligns perfectly with our everyday expectations of cause and effect. But when we begin to examine the phenomenon of Hawking radiation, a very peculiar detail emerges. The most critical aspect of this radiation, for the purpose of our discussion, is that it is non-local. This means it does not originate from the black hole itself, but rather from the region of space that surrounds it. To be clear, the origin of this radiation is not within the singularity of a black hole, nor is it even inside the dark sphere we visualize. That interior region is difficult to define in any conventional sense, as space as we understand it ceases to exist there. The dark sphere we imagine is simply the event horizon, the threshold separating a region of escapable space-time curvature from one that is inescapable. And what's intriguing is that this process doesn't even occur right at the edge of the event horizon, despite common portrayals of the theory. The popular image is often of two particles spontaneously appearing at this boundary, where the antimatter particle is just inside and falls in, while its normal matter counterpart is just outside and escapes. This, however, is not an accurate picture of what happens. Instead, the volume of space where this radiation can emerge is vast, extending for a distance several times the size of the event horizon, potentially reaching out for billions of kilometers. When we consider that the largest known black holes are immense enough to contain multiple solar systems side by side within their event horizons, the idea that a photon could materialize that same distance again beyond the horizon is truly staggering. This phenomenon can take place in a location where there is essentially nothing at all. In essence, Hawking radiation does not come from the black hole itself. It is instead generated by the curvature of space created by the black hole, and this can happen remarkably far away from the object. But if this is true, it implies a chain of events that operates in complete opposition to our everyday expectations. Consider the sequence in this order. As energy departs from the curvature of space, that curvature must lessen, a direct consequence of the conservation of energy. And as this reduction in curvature occurs, the black hole then shrinks. This is a profoundly counterintuitive idea, almost like a footprint in the sand shrinking, which in turn causes the foot that made the print to become smaller. It feels fundamentally wrong, as if cause and effect have been reversed. And yet, Einstein himself hinted that such a possibility might exist. In one of his equations, he showed that the curvature of spacetime was proportional to the mass energy of an object. But to be proportional is not the same as to be causational. There is no built-in assumption in this relationship that one must cause the other. We are quite comfortable with the concept of changing an object's mass and thereby changing the curvature of space around it. However, the mathematics work just as validly in the other direction, where changing the curvature could in fact change the mass. If this holds true, it points toward a universe where mass itself might be merely a projection, an effect caused by the curvature of space. Imagine shining a light at your hand, casting a shadow on a wall. That shadow is a projection, its existence caused by your hand interacting with the light. In this analogy, one might naturally assume that we are the hand, that our mass is the tangible thing creating the curvature of space around us. But what if we have it backwards? Could it be that we are simply the projections, shadows cast upon the wall of the universe, brought into being by something far more fundamental happening within the curvature of space-time, all while we perceive ourselves as the solid, primary reality? The truth is, we do not know for certain. Given that your entire reality is based on what you experience, it would be exceptionally difficult to distinguish between these two scenarios. But if there is one lesson to be learned from relativity, it is that if no experiment can tell the difference between two situations, then we cannot entirely dismiss the possibility that we are in one and not the other. It could also mean the two concepts are more deeply intertwined than we ever imagined. Of course, it is important to remember that this is all a theory. There is no definitive proof that Hawking radiation is a real phenomenon, though some experiments have offered hints that it might be. It remains, for now, a fascinating concept to contemplate. Even if it were proven that our reality is a projection, it would not likely alter the course of your day. You would still think and feel, and that experience is more than enough reason to continue on as you are. But it serves as a powerful example of how, when we begin to investigate the fundamental architecture of reality by studying the extreme warping effects of black holes, we can be forced to challenge our most basic assumptions about our own nature. After all, when you ask the question, "Am I real?" and the answer from physics is, "It's not entirely certain," that is more than a little unsettling. In either case, black holes influence our reality and our universe in profound ways, and not just because they draw everything within their grasp into them, never to return. They represent an endpoint, the ultimate destruction in the cosmos. And yet, what if they could also be our salvation? It is possible that black holes hold the key to traveling faster than the speed of light and to solving our energy crises in ways that were unimaginable until very recently. And as we have come to see, they seem to do this by manipulating the fabric of reality itself, often in ways that completely upend our expectations of physics. Perhaps our entire way of thinking about black holes has been incomplete. But to understand how a black hole might bypass the usual limits on faster-than-light travel, and do so in a way that could be harnessed without ever crossing its event horizon, and how it could simultaneously produce nearly infinite energy, we must first understand more about its fundamental properties. It is actually quite difficult to say much about a black hole's features. Precisely because of the event horizon, we are prevented from ever seeing what a black hole looks like on the inside. In fact, there are only 3 characteristics we can state about any black hole with a high degree of confidence. It has mass, it has charge, and it has angular momentum. You might wonder how we can know these things, given that no light can escape to carry this information to us. The key is that each of these 3 properties represents an aspect of the black hole that can be detected outside its event horizon. Charge, for example, behaves around a black hole just as it does around any other charged object. This means that a charged black hole will attract objects with an opposite charge and repel those with a similar charge. You can think of it as a vast, invisible source of influence, pushing and pulling on the cosmos around it. Scientists can observe objects approaching a black hole, and by measuring how known charged particles are accelerated toward it, they can infer the charge of the black hole itself. Interacting with this property is the black hole's mass. The influence of a black hole's mass can be perceived well outside the boundary of its event horizon. In a fundamental sense, this mass is the very architect of the event horizon itself. This relationship exists because mass generates gravity, and it does so in a predictable, linear way that follows principles analogous to a theorem in electromagnetism known as Gauss's law. Consequently, it becomes possible to deduce an object's mass by observing the behavior of other objects nearby. One can measure the distance at which they begin to accelerate toward it, and then track the rate of that acceleration. Of course, for such calculations to be accurate, any electrical charge must also be taken into account. Otherwise, the results could be significantly distorted. The final observable property is its angular momentum, more commonly known as spin. It is indeed feasible to detect the rotation of a highly massive object, and the method for doing so is a fascinating topic we will explore shortly. For the moment, we can accept this as a given and simply acknowledge that black holes are objects of truly immense mass. Black holes exist across a vast spectrum of sizes. The very smallest, referred to as micro-black holes, possess a mass comparable to our own moon, or about 7.35 times 10, 22 kilograms. What's remarkable is that they concentrate all of this substance into a volume just 0.2 millimeters across. This detail provides a profound sense of the incredible density involved, an object smaller in diameter than a human hair, yet containing the entire mass of the moon. And these are merely the smallest examples. Stellar black holes typically have a mass equivalent to 10 times that of our Sun, contained within a diameter of 60 kilometers. Further up the scale are intermediate black holes, which can be as massive as 1,000 suns, yet they compress this into a sphere with a diameter of 2,000 kilometers, a size still smaller than our own planet. It is the largest black holes, however, that truly humble our sense of scale, with masses ranging from 100,000 to an astonishing 10 billion times the mass of the Sunday. Their sizes span from 0.001 to 400 AU, where 1 astronomical unit is the distance from the Earth to the Sunday. Beyond these 3 defining characteristics, theory suggests there are no other distinguishing features. If one were to place 2 black holes side by side, ensuring they had identical mass, charge, and spin, they would be fundamentally indistinguishable from one another. Yet these 3 properties are more than sufficient to create some extraordinary effects on the fabric of space just outside the black hole. While traveling into a black hole is impossible, as both space and time cease to function as we know them past the event horizon, we believe we have some understanding of what must exist within. Deep in the core of every black hole, there is thought to be a singularity. In reality, this singularity times the black hole. The diameters mentioned earlier were merely measurements of the event horizon's boundary. It's important to remember that we are not entirely certain what a black hole truly looks like, since no light can ever return from it. The concept describes a point within an infinitely small space where all the black hole's mass is compressed, resulting in infinite density. In the simplest models of non-rotating black holes, this singularity is a single, dimensionless point. For a spinning black hole, the picture changes to something more like a tiny, rotating ring. Otherwise, defining spin for a point with no volume would be a conceptual challenge. Our current understanding of physics becomes profoundly strange in the vicinity of such an object. If one were to follow certain ideal paths around this point, it becomes mathematically plausible to achieve bizarre outcomes, such as intersecting with one's own past. This raises unsettling questions about causality and leads to temporal paradoxes, like the famous grandfather paradox, which likely indicates that our current ideas about singularities are not yet complete. The infinitesimal nature of the singularity means that a true explanation will require a successful unification of quantum theory and general relativity, a goal we have not yet achieved. It remains possible that future discoveries will reveal that singularities do not exist at the heart of black holes at all. For now, however, this represents the frontier of our knowledge. Whatever resides at the center of a black hole, it is the source of its immense power, because like most objects in the cosmos, it rotates, and its rotation is profound. As we imagine a journey outward from the center, we would cross the event horizon with very little local drama. The event horizon is not something that can be detected as you pass through it. Although an external observer would see you appear to slow down and freeze in time, from your own perspective, time might seem to be flowing perfectly normally. That is, until the entire future of the external universe unfolds in an instant, a consequence of time outside the black hole passing incredibly fast relative to your own. This is the core principle of relativity. In fact, the only clue that you had crossed the event horizon might be the existence of something just beyond it, the photon sphere. In a region just outside the event horizon, there is a precise zone where a photon entering at the perfect angle will become trapped in a stable orbit around the black hole, much as the Moon orbits the Earth. This infinitesimally thin region is the photon sphere, and considering the countless photons that have passed by black holes over millions of years, it is likely saturated with light energy. It is quite plausible that any object passing through this sphere would be instantly vaporized. Just outside this intense boundary, however, we find the region that holds our interest. This is the ergosphere. The ergosphere is the area around a black hole where its spin becomes most tangibly apparent. This is because, within this zone, it is physically impossible to remain stationary. We know that mass affects space, which we observe as the curvature of gravity influencing how objects travel through it. A more precise way to describe this might be to say that mass drags the space around it. As an object moves, it pulls a small amount of the surrounding spacetime along with it. When an object as massive as a black hole spins, this effect, known as frame dragging, becomes extreme. To put it simply, reality itself around the black hole is forced into a swirling vortex that cannot be resisted. Much like a real whirlpool, anything caught inside the ergosphere is compelled to circle the black hole because the very frame of reference it occupies is being pulled along. This is similar to how a person on a moving walkway is carried forward with it. The greater the spin of the massive object, the faster this dragging of spacetime occurs. Within the ergosphere, this effect can accelerate to such a degree that, by the time you reach the event horizon, space itself is moving faster than the speed of light. To remain at a relative standstill from the perspective of a distant observer, you would need to travel faster than light in the opposite direction, a feat which is, of course, impossible. This seems to raise a fundamental question about the laws of physics. Doesn't Einstein's work establish that nothing can travel faster than the speed of light? The answer is indeed yes, but black holes appear to exploit a remarkable loophole in this cosmic rule. You see, the light speed limit is a local constraint. In your immediate frame of reference, nothing can surpass the velocity of light. However, the principles of relativity permit different frames of reference to move apart from one another at such immense speeds that, from a distant viewpoint, objects within them can appear to violate this barrier. If you were to travel to that distant frame and enter it, the objects would seem to slow down, once again conforming to the known laws of physics. It is a profoundly strange effect, but this phenomenon, known as frame dragging, is a real and measurable aspect of our universe. In fact, it is by measuring the degree of frame dragging that astronomers can determine the spin of a black hole. According to the physicist Roger Penrose, there might even be a method for harnessing this effect. He proposed that if a spacecraft were sent into the ergosphere, it would be swept up in this swirling vortex of spacetime, causing it to accelerate dramatically. Once it had acquired sufficient velocity, The craft could then jettison some mass or fire propellant in a calculated direction, allowing it to escape the whirlpool with significantly more energy than it possessed upon entry. This theoretical technique, named the Penrose process, could hypothetically generate a net energy gain equal to about 20% of the spacecraft's mass. While that number might not initially sound substantial, one must consider Einstein's equation, E equals mc squared. In this context, that 20% of mass would be converted into an amount of energy equal to itself multiplied by 299,792,458 squared. The resulting energy yield would be truly colossal. To tap into this extraordinary kinetic energy, one would theoretically only need to journey to the nearest black hole, approximately 3,000 light-years from Earth, and guide a vessel capable of withstanding the intense gravitational forces into its ergosphere. Ideally, one would also need to select a black hole that is not encircled by an accretion disk. These disks can reach temperatures of millions of degrees as their constituent matter is accelerated to near-light speeds, melting from solids into gas and plasma. The concept is clear, though its execution is perhaps less than simple. For us, this remains a highly impractical endeavor. Even so, the implications for faster-than-light travel that black holes reveal through frame dragging could one day provide the key to genuinely surpassing the light barrier. The solution may not involve propelling an object faster than light, but rather finding a way to compel its entire frame of reference to travel at those speeds, just as spacetime does around a black hole. Of course, if such a feat requires the energy of a black hole itself, we may be far from achieving it. Yet it offers a breathtaking glimpse into what is physically possible, and scientists are already investigating the power of frame dragging for future modes of travel. This entire line of thought serves to highlight, once more, how profoundly different our universe is from what we might have imagined. And there is another surprising aspect of black holes that may be unfamiliar. Falling into one is considerably more challenging than it sounds. One might naturally assume the process would be quite simple. Are these not the ultimate cosmic absorbers, the most powerful sources of gravity in existence? Shouldn't it be easier to fall into them than into any other object in the universe? While this line of reasoning seems logical, it is paradoxically incorrect. These galactic voids are among the most difficult places in the cosmos to actually enter. This difficulty is so significant that during his lifetime, Einstein held the belief that nothing could ever get inside one. Not only that, but black holes can even eject matter away from themselves at velocities approaching the speed of light. It seems counterintuitive that these objects would be anything but incredibly easy to enter. One might picture a slide that grows ever steeper, causing an object to accelerate more and more as it nears the black hole's center. While this analogy holds some truth, it is also misleading. An object does indeed accelerate to tremendous speeds, approaching that of light itself. However, in nearly all circumstances, this acceleration does not guide the object toward the black hole's core, and this is not a reference to some esoteric quirk of time or relativity, but rather an observable reality from any frame of reference. The explanation for this phenomenon can be found by examining a real-world feature called an accretion disk. At their core, black holes are remarkably simple. According to a principle known as the no-hair theorem, black holes are characterized by an almost complete lack of features. Their identity is defined by just three properties. They possess charge, mass, and spin, and that is essentially all. Consequently, accretion disks are not a necessary component of a black hole. They can exist perfectly well without them, as dark, unobservable points in space. However, when matter, such as an errant star, wanders too close to a black hole's gravitational field, it can be torn asunder by the immense tidal forces and pulled toward the center. Yet, what is intriguing is that this material does not immediately cross the event horizon. Instead, the matter typically coalesces into a flattened, ring-like structure that orbits the black hole from the outside. While this material does eventually fall in, the process can take an extraordinarily long time. Some accretion disks are known to persist for 100 to 1,000 million years before being completely consumed. So, what is occurring here? Why does the matter not simply plunge into the black hole? The answer is rooted in a fundamental principle of physics known as the conservation of momentum. First described by mathematician John Wallis in 1670, and later refined by his contemporary Newton, the concept is straightforward. For any isolated group of objects, the total amount of motion, or momentum, must always remain the same. If a particle with momentum collides with a stationary particle and they both bounce away, the total momentum of the two particles afterward must equal the initial momentum of the first particle alone. No momentum can be created or destroyed. Consider a rocket on a launch pad with zero momentum. It can only generate upward momentum by expelling propellant with an equal and opposite downward momentum. When you sum the downward momentum of the exhaust and the upward momentum of the rocket, the net result is zero, preserving the system's original state. This principle operates far beyond our everyday expectations, governing the universe on every scale. At first glance, the law of momentum conservation might seem at odds with our daily experience. After all, we humans start and stop moving without any obvious obedience to this rule. Yet, when every interacting particle is accounted for, the law holds perfectly true. We would find it impossible to walk without a surface to push against. The forward momentum we gain is perfectly balanced by an equal and opposite momentum transferred to the planet itself. We simply don't perceive the Earth's resulting motion because its mass is so immense compared to our own. This principle, however, has profound implications for an object falling into a black hole. To understand why, a different form of this law, concerning angular momentum, is a useful guide. A classic illustration is a ballerina executing a spin with her arms extended. The particles comprising her hands possess momentum as they travel a specific distance over a certain time. When she suddenly pulls her arms in close to her torso, a noticeable change occurs. Her rate of spin increases dramatically. This is a direct consequence of momentum being conserved. The momentum in her hands effectively tries to maintain its original speed, but now that her arms are closer to her body's axis of rotation, that speed is applied to a much smaller circular path. With less distance to cover for each revolution, each turn is completed far more quickly. This physical reality is what causes the ballerina to accelerate her spin when her arms are tucked in and to decelerate when they are stretched out. Now, let us envision this same dynamic playing out on an astronomical scale. In nearly every case, inbound material does not travel on a direct path into the black hole. It almost always arrives with a slight offset, causing it to be captured by the black hole's gravity and begins spiraling inward. At this point, it possesses angular momentum. As this matter draws nearer to the black hole's center, its orbital path shrinks, and just like the ballerina, it must spin faster and faster. To fall just a little bit closer, it is forced to rotate a little bit more rapidly. But unlike the ballerina, this cosmic matter is constrained by the speed of light. Albert Einstein established that nothing in the cosmos can exceed this ultimate velocity. So, what becomes of this swirling material as it descends deeper and deeper toward the black hole? Subjected to colossal forces and the extreme curvature of space-time, it ultimately reaches a point where it physically cannot move any faster. It confronts an absolute cosmic limit, and because it cannot increase its spin, it can no longer continue its inward fall. This impasse has several extraordinary effects. First, as one might expect, it generates immense friction. All of this material, orbiting at unimaginable velocities just outside the event horizon, creates a maelstrom of high-energy collisions. When these interactions happen at near-light speeds, conditions become incredibly hot. Matter within a black hole's accretion disk can soar to temperatures of 10 million Kelvin, a heat so intense it strips atoms apart into a glowing plasma. These perpetual collisions batter the atomic particles, forcing them to radiate away more and more of their energy, much like squeezing water from a sponge. The intriguing detail is that this process reduces their mass. Between 10 and 40% of an atom's mass can be converted directly into energy and broadcast across the universe. For perspective, nuclear fusion, the very process that powers our sun, converts only about 0.7% of mass into energy. The sheer efficiency of the accretion disk is staggering. If our sun is so brilliant at 0.7% efficiency, one can only imagine the luminosity of a black hole's accretion disk. The most radiant of these disks are known as quasars, and their brightness can be more than 1,000 times greater than the combined light of every single star in our Milky Way galaxy. Fortunately for the trapped matter, some of its angular momentum is carried away with this departing radiation. More momentum is shed by being transferred to material orbiting further out in the disk, as faster particles collide with slower ones just above them, providing an outward push that slows the inner particles down. Through this process, matter gradually loses its angular momentum and can finally resume its descent into the black hole. Additional momentum can be expelled through one of the most visually stunning phenomena associated with quasars and black holes, their jets. Our understanding of these jets, how they are formed and what they are made of, is still developing, and they appear only in a small fraction of black holes that have accretion disks. Current theories propose they are driven by powerful magnetic forces generated either by the spinning disk itself or by the rotational energy of the black hole. It is likely that as the electrically charged particles in the accretion disk swirl, they generate magnetic fields in accordance with Ampere's law. The power and configuration of these fields are thought to create a narrow escape route for particles at the black hole's north and south poles. These magnetic fields may work in a way analogous to the rifling inside a gun barrel, funneling particles into a tightly focused beam. For particles moving at near relativistic speeds, this channel may be the only direction they can travel. Perhaps they are ejected like steam from a kettle, forced out through the only available opening in the face of such overwhelming gravitational and thermal pressure. And when these particles are launched, their journey is immense. Relativistic jets can extend far beyond the galaxies they originate from, often stretching for millions or even billions of light years. One such jet, from a source designated PSOJ 352, 4034-15, 3373 or PJ 350-15 for short, sends X-rays that, while faint, can be detected on Earth from a distance of 12.7 billion light-years. The radiation from these jets is highly concentrated in one direction, due to an effect called relativistic beaming, also known as the lighthouse effect. The jet is much more difficult to observe when it is pointed away from us. A clear example can be seen in the famous M87 galaxy, where the Hubble telescope has captured a distinct relativistic jet. This is the beam aimed in our direction. A second jet is almost certainly erupting from the opposite pole, but because it is moving away from us, it remains invisible. It is crucial to remember that this energy does not originate from within the black hole. Nothing, not even light, can escape its grasp. Instead, all of this matter and radiation is unleashed by the accretion disk that surrounds the black hole. And once again, much of our knowledge about these jets remains theoretical. We can see them and even track their movement over time, but a complete understanding of what they are and what truly powers them still awaits discovery. Our understanding of accretion disks still contains unresolved questions, particularly regarding the conservation of momentum. A lingering mystery remains as to where all of this rotational energy ultimately goes. The sheer potency at play, however, is impossible to deny. It was once thought that falling into a black hole might be impossible, but it is now evidently a reality. Yet, when certain black holes are observed ejecting powerful jets of matter at nearly relativistic velocities across distances that span entire galaxies, it becomes clear that not falling into them is also a distinct possibility. When one also considers the immense outward force of matter heated to millions of degrees, all pushing away as it attempts to shed its own momentum, the idea of approaching one seems increasingly unwise. We have seen how the profound influence of a black hole can extend across a whole galaxy, which naturally leads to the question of just how large one of these objects can become. Locating the most massive black holes is not an especially difficult task. The search invariably leads to the centers of large galaxies. These supermassive black holes have been growing since they first formed billions of years in the past. As more and more material succumbs to their gravity, their mass continuously increases. The most dominant of these can achieve masses billions of times greater than that of our own Sunday. A curious paradox emerges, however, when we realize that some of the most colossal black holes ever identified are also, from a certain point of view, the youngest. When we observe distant galaxies, we are simultaneously looking back into the past. For galaxies that are billions of light years away, the light we see has taken billions of years to travel to us. Given that the universe is only 8 billion years old, a galaxy observed from such a distance can only be a few billion years old from our perspective, which is quite young for a galactic structure. It would seem logical that supermassive black holes in nearby, and therefore older, galaxies should be more massive, having had so much additional time to accumulate in falling matter. So, what exactly is happening here? The largest supermassive black hole currently known is an object designated TON 618, which possesses a truly staggering mass of 66 billion solar masses. Its mass alone is comparable to that of the entire Milky Way galaxy. Yet, TON 618 is located at an exceptional distance, and the light from it has traveled for 10.8 billion years to reach our telescopes. This means we are observing this object as it existed 8 billion years ago, giving it a maximum possible age of around 2.8 billion years at that point in time. For comparison, our own Milky Way galaxy is approximately 13.6 billion years old, yet the supermassive black hole at its core, Sagittarius A*, is a mere 4 million solar masses. While the supermassive black hole in the Andromeda galaxy is larger, it still only amounts to about 200 million solar masses. One of the significant factors to weigh here is the inherent difficulty in detecting and measuring black holes. This area of research is still in its relative infancy, as the necessary technology has only enabled us to begin observing these objects within the last few decades. Even with modern instruments, we can often only study the region immediately surrounding a black hole, at least before the advent of the Event Horizon Telescope. And even this powerful tool requires immense time to produce an image of a single black hole, meaning our general understanding remains quite limited. In fact, most of the distant black holes we are aware of are only visible because they are quasars. TON 618 is one such quasar. An incredible volume of matter is spiraling into its accretion disk, causing it to erupt with phenomenal energy. A quasar can only maintain this state as long as it is actively feeding on matter. Otherwise, it fades back into a dark, invisible black hole. While the physics of the accretion disk are not fully understood, it is thought that the friction generated within it is so extreme that a quasar's disk alone can produce thousands of times more light than all the stars in its host galaxy combined. TON 618, for instance, generates the light equivalent of 140 trillion suns, completely overwhelming the galaxy it inhabits to the point that the galaxy itself is invisible from our vantage point. Because quasars are the most luminous objects in the cosmos, they can be seen from extraordinary distances. Consequently, one reason the largest known black holes appear to be so far away is due to an observational effect known as the Malmquist bias. This principle highlights that, as we look deeper into space, our view becomes skewed toward the most brilliant objects, simply because they are the only ones we are able to detect. This implies that our sample is not representative, and that the largest supermassive black holes may actually be distributed more evenly throughout the universe than they appear. If a distant galaxy hosts a very large black hole that is not an active quasar, we are unlikely to see it, as a galaxy is far dimmer than a quasar. A second reason we do not observe the largest black holes in our local universe relates to the conditions of the cosmos shortly after the Big Bang. As the universe continues its expansion, it is worth remembering that in its early stages, matter was packed together much more densely. Quasars were more prevalent then because they require an extreme influx of matter to radiate so brightly, and there was simply much more available gas in the early universe. Not only has the universe expanded since then, but over eons, much of that primordial gas has been converted into stars. Some of the most massive stars eventually collapse into neutron stars and black holes themselves, meaning their material is never recycled back into interstellar gas. A reduced supply of available gas means less of it will fall into a supermassive black hole. One of the theories about the ultimate fate of the universe, known as the Big Freeze, is based on this process, suggesting that after trillions of years, all available gas will be locked away inside black holes. Even today, we can observe galaxies where the gas has been completely exhausted, preventing the formation of any new stars. These are known as elliptical galaxies. Spiral galaxies, by contrast, still possess structures of gas and dust, and can therefore continue to produce new stars. It is an intriguing detail that most of the largest supermassive black holes seem to reside in elliptical galaxies, where little to no free gas remains. For gas to fall into a galaxy's central supermassive black hole, it must first lose its angular momentum. In elliptical galaxies, this process appears to have already occurred on a massive scale, which would explain why their central black holes are so large. In spiral galaxies, this has not happened to the same degree. A trigger for this loss of angular momentum could be the gravitational influence of a nearby galaxy, or even a direct collision between two galaxies. Furthermore, there is simply less gas available throughout the universe today than there was in its youth. This suggests that the growth of black holes likely happened much more rapidly in that early era and has since slowed considerably. This might be why there are no quasars found within a radius of 500 million light-years of Earth. As the universe aged and grew more diffuse, active quasars became increasingly rare. Consequently, the quasars we can observe, which include some of the most massive black holes ever found, are all from a much earlier time. This raises an interesting question. Why do the largest supermassive black holes appear to be the most ancient? The truth may be that this is an illusion, not the full reality. We can measure distant, bright quasars precisely because their light is powerful enough to reach us. It is quite possible that older, closer black holes are also enormous. However, an effect known as Malmquist bias means we have not yet discovered them. As our studies progress and technology evolves, a more complete picture of the cosmos around us will begin to form. This journey has covered many essentials of black holes, yet much more is almost certainly left to be discovered. What stands out is how they have completely reshaped our concept of what is normal in the universe. We are grateful for the support from our patrons and members. For those interested, more information can be found via the links in the description. We look forward to our next exploration together.